in this video we're doing Calc AB problem set 133. This will actually be the final problem set that I do on a daily basis. I don't know what I'm doing after this, but anyway, the problems and the playlist are in the description below. Let's see what we're doing. Number 1, 5-foot tall person walks away from an 18-foot tall street lamp at a rate of 3 feet per second. We want to find the rate at which the person's shadow grows when the person is 12 feet from the lamp. Let's draw a picture. So this is just going to be similar triangles. This is the classic shadow problem. Let's fill in the things we definitely know. So we got 5 feet, 18. Let's fill in some variables for things that can change. Let's call the distance between the person and the lamp x. And then the shadow itself is y. So we are trying to find dy dt when x is equal to 12. That's the problem that we're trying to solve. We also know that dx dt is 3 because that's the rate at which x is growing. All right, so I'm going to do some similar triangles. I'm going to start with the biggest triangle. I'm going to do the horizontal distance, which is x plus y, over the vertical distance, which is 18. Should be equal to, look at the smaller triangle, y, the horizontal distance, over 5, the vertical distance. So we have this. It's easier if you rearrange this. So I'm going to multiply through by 5 and multiply by 18 and get this. Keep going, get that 5x is 13y. And so we definitely know that 5 over 13x is equal to y. Now what we need to find is the derivatives with respect to time. So dy dt is going to be 5 over 13 dx dt. And dx dt is that rate that we were given. So we know that this is 3. So dy dt is going to be 5 over 13 times 3. And so that's going to be 15 over 13. And then our units are going to be feet per second because it's still just a linear thing. Now, there's another way that you can do this. I never think to do it initially, but if you add in the horizontal line from the person's head across to the lamp, that's going to have a length of x, and the vertical is going to be 18 minus 5, which is 13. The two little triangles are similar by angle, if you care about that, but it's y over 5 is equal to x over 13. This is like a more direct way of solving this problem. Not that the problem is super challenging the other way, but this is definitely more direct. And this takes us right to this step. You're going to get the same answer. Good problem. That's the shadow problem. It's a classic. I once screwed up and told my students that it wasn't worth going over right before the exam, and then it was literally on the exam. So that's why I put it on this problem set. All right, let's look at the next one. If f and g are differentiable functions such that the tangent to f at x equals 3 is y equals 5x minus 9, while the tangent to g at x equals 6 is y equals 7x minus 37. We want to find the limit as x approaches 3, f of x minus 6 over g of 2x minus 5. Okay, so first things first, I'm going to, from the tangent lines, just get like the values that we know, right? So the tangent at 3 is 5x minus 9, so we can find f of 3 by plugging in 3 there, right? 15 minus 9 is 6. We can find f prime of 3 by using the slope, right? It's just 5. Do the same thing for g, but at 6, which is kind of weird. So g of 6 is going to be 42 minus 37, which is 5. G prime is going to be 7. Okay, so we know these things. That means that if you just directly substitute into the original limit, we get f of 3 minus 6 and g of 6 minus 5. That's 0 over 0. This is a L'Hopital's problem, so now, because it's open-ended, we have to like establish everything. So we know the functions are differentiable. We know that means they're continuous, which means that the limits equal the value of the function. I'm going to write that down. So f of x is differentiable, which implies continuous. Therefore, the limit as x approaches 3 is equal to f of 3. And f of 3 we just found was 6. I'm going to do the same thing for g, but I'm doing it at, I'm doing it the limit as x approaches 3, but it's going to become g of 6, right? So g is differentiable, which means continuous. Therefore, the limit as x approaches 3 of g of 2x is equal to g of 2 times 3, g of 6, which we just said was 5. This is what allows us to say that the limit of the numerator and denominator are both equal to 0. So I'm going to write that, which means that we're allowed to use L'Hopital's. So by L'Hopital's, the original limit, we actually are going to do it. So derivative of the top over derivative of the bottom. So it's going to be f prime over 2g prime of 2x. And then we plug in 3, or we take the limit as x approaches 3, but this involves just plugging in 3. We get this, And these are the values that we found, so it's going to be 5 over 2 times 7, so it's going to be 5 over 14. Good L'Hopital's problem to kind of close it out. We got one more that we're going to do. We want, and also I made a mistake on it, so I had to correct that. You can see that little y there. If dy dx is equal to 6 minus 5y, and y is equal to 4 when x is equal to 1, what is y when x is equal to 3? Okay, let's solve this. First thing is, I do not like to do separation of variables with a negative coefficient for y, so I'm going to factor a negative out on the right-hand side. So dy dx is going to be the negative of the quantity 5y minus 6. Now, separate. I'm going to leave the negative 1 on the right-hand side, get negative 1 dx, or just negative dx. I'm going to throw in some integral signs. On the left-hand side, there should have been a 5 in the numerator by the chain rule, so I'm going to put a 5 and then balance it with a 1/5. Get 1/5, natural log, absolute value, 5y minus 6, equals, integrate this, we get negative x plus c. Okay, so I'm not going to try to solve for c here because there's a natural log. There's also a 1/5, so I'm going to multiply both sides by 5 and just get natural log of the absolute value 5y minus 6 is negative 5x plus, I just say c, I change the color, it's actually a different c, right? This c that we just found is going to be 5 times the previous c. It really, when you decide to solve for c, it does impact what you get for c, but the final result when you solve for y will be the same. So this is a new c, new color. I'm going to now exponentiate because it skips the issue of the absolute value. So exponentiating gives me 5y minus 6 equals a new c, so a new color, e to the negative 5x. Now I think I'm going to try to solve for c. We know that x is 1, y is 4. So this will be 20 minus 6 is 14 is c e to the negative 5th. Great. So c is going to be 14 over e to the negative 5th, or I'm just going to write it as 14e to the positive 5th, which means that our function, when we substitute, we get 5y minus 6 is 14e to the 5th times e to the negative 5x. This you can simplify like quite a bit. So properties of exponents gives us 5y minus 6 is 14e to the negative 5x plus 5. And then I'm going to add 6 and divide by 5. That's going to tell me what y is equal to. So add 6, divide by 5. Now, we are really being asked, what is y when x is equal to 3? So we need to take 3 and plug it in for x. It doesn't give you a nice looking answer, but y when x is equal to 3 is going to be 6 plus 14 e to the negative 10th over 5. That's our final answer. That is the final problem on the final problem set. I hope these were all helpful. Good luck.